Welcome back, dear friends. This is an interesting video on one of the very important topic, especially for the people in industry who deal with the practical systems of refrigeration and air conditioning. So the topic, I would name it as multi-pressure system. Multi-pressure in the sense that it would involve more than two pressures. Let me just explain you this for a moment. You know that the conventional vapor compression system, conventional refrigeration system, it has a evaporator and a condenser which operate at corresponding pressures. That is, the condenser is at a higher pressure and the evaporator is at a lower pressure. The pressure difference is maintained by the compressor and expansion device respectively. So why do we go for a multi-pressure systems? Now one can think of a multi-pressure system as either a multi-evaporator system. I'll be explaining you, don't worry about it if you don't understand these terms. One is a multi-evaporator system, which could come under a multi-pressure system. And the other important one could be called as the multi-compressor system, or it is popularly known as multi-staging compressor system. Okay. Now, what exactly these systems are and why do we use these systems? This is to be understood very clearly. To understand this very clearly as to why do one require a multi-evaporator system and multi-staging compressor system, we need to go back to our basics. Basics, I mean the understanding of vapor compression refrigeration system. The pH diagram I'm trying to draw here, look at this, look at the screen. This is the vertical axis representing the pressure, and this is the horizontal axis representing the enthalpy. So the pressure enthalpy diagram, this is the pressure, and this one is enthalpy. This is the vapor dome. This is vapor dome. And let me draw the two pressures. One is the higher pressure, that is a condenser pressure, and the lower pressure, which I could call it as the suction pressure or the evaporator pressure. So this diagram one is familiar with when you study the vapor compression refrigeration system. So this system, that is 1 to 2, 3 and 4, is the representation of simple vapor compression refrigeration system. The system, this system you'll find widely used in many refrigeration applications. For example, in domestic refrigerators, in window air conditioners. Let me just list down those applications, like the one which you are familiar with, domestic refrigerators. It has got the simple vapor compression refrigeration system. I mean, there is a single compressor, there is a single evaporator and a single condenser. A window air conditioning system, window AC or a split AC, also you will find that there is a single compressor, single evaporator and a single condenser. Okay. Similarly, larger systems also you will find that they are two pressure systems. When I am saying that we need to understand what is multi-pressure systems, either we can think of two or more evaporators, or we can think of two or more compressors with the intercooling in between. Two or more evaporators would be a multi-evaporator system, and two or more compressors would be a multi-staging system. Obviously, when you are talking about a compressor systems having two compressors or more compressors, it essentially involves intercooling. So we'll be coming to this concepts of intercooling and why this intercooling helps and when it is to be used. But before that, let me just point out that these systems, multi-evaporator systems and multi-compressor systems, they are useful especially when you are talking about extremely low temperatures. Like for example, I'm talking about extremely low temperatures for freezing applications or liquefaction of gases. Okay. And let us say for your freezing applications, you would need to take the evaporator to minus 50 degrees centigrade. And for liquefaction, one might need to take it to minus 150 degrees centigrade. Okay, so these are the typical values. You can remember those. For let us say food freezing, the evaporator temperatures are minus 40, minus 50s like this. And for liquefaction, that is converting the gases to liquid, one might encounter a lower temperatures. Okay, liquefaction of gases. So this temperatures when you are encountering, what happens is when you are using, suppose for example, if you are using a you are using a single stage system, that is this system, then what would happen is the evaporator temperature would lower. When one is going for application like this, the evaporator temperature lowers, and when the evaporator temperature lowers, it would adversely affect the performance of the system. So at very low temperatures, one would encounter losses and the coefficient of performance would be reduced. Similarly, not only that, the compressor discharge temperature, this is the discharge temperature. These temperatures are also higher and that might affect the life of the compressor. Okay. There are a number of disadvantages. The third could be the throttling losses. The throttling losses would be more. What are the throttling losses? That we would be discussing in detail when we discuss this multi-pressure systems. So let me just list down what would happen if you are talking about a single stage system or a two pressure system for applications like. So one is the losses could be more in throttling. Mind well that we have not yet discussed what are the throttling losses. Okay, we are simply saying that during throttling there would be losses. Throttling means expansion. We would say that there would be losses because of and that would be losses as well as operational issues because of high discharge temperatures. In the figure, it is shown by T2. Okay, so high compressor discharge temperature. This is also not desirable. So this is one of the major disadvantage of using a two-stage systems. Okay, discharge temperatures. The third could be like, for example, this is called as if you are going for a single stage system, there would be losses in this section, right? And there would be losses even when you are talking about a lower pressure. There would be an increase in the specific volume at the inlet to the compressor. So this means, for example, if this is 1 and this is 1 dash, so the specific volume 1 dash would be greater than V1, and that is not desirable. Okay, so all these factors, when you are encountering extremely low temperatures, would encourage us to move towards a multi-pressure systems. Okay. Similarly, for example, if we are having let us say an application where you need to use a single evaporator you need to achieve ASC application and food freezing application simultaneously. Okay, so in that case we need to use two evaporators. Okay, so then in that case, if you want to use a single condenser and you want to cater to two different temperatures, one is for AC, which obviously would require a higher temperature, and other is for food freezing, which would require a lower temperature. In that case, one would go for a multi-evaporator system. So we need to be very clear that multi-pressure systems are used when we are encountering a higher pressure ratio. By higher pressure ratio, I mean the condenser pressure upon the evaporator pressure. Okay, so the condenser pressure upon the evaporator pressure, typically the thumb values are, if the values are greater than 4 or 4 to 5, then it is desirable to go for a multi-pressure system. Okay, so this is a thumb rule. So please remember this number, that if the ratio, obviously the condenser pressure is always higher, but if that ratio, that is the condenser pressure to the evaporator, if it evaporator pressure ratio, if it happens to be 4 or greater than 4, then it is desirable to opt for the multi-pressure systems. And by multi-pressure systems, as I said, either it could be a multi-evaporator system or a multi-staging system with intercooling. Okay, so with this introduction, let me move to the specific systems, that is the multi-evaporator systems and multi-staging systems. For discussing multi-staging systems, okay, we need to revise our concepts of compressors. Let us say that we talk about a compressor, and so when you are talking about intercooling, let me move to the other slide. Let us revise what we had learned about compressor, and especially when you are talking about the savings because of intercooling. Okay, so by intercooling, what I mean is, let us say there are two compressors. And in order to achieve the required final pressure, that is the discharge pressure, what we do is that we first compress the refrigerant in a single stage in a low pressure stage compressor. Then by some method we intercool that refrigerant, and then again we compress it. Okay, so this is a pressure volume diagram I have drawn. So this diagram, if you look carefully, what one would understand is, looking at this diagram, let me just label those. Let us say that the initial stage, that is entry to the compressor, is 1. Exit to the low pressure compressor is 2. Then there is some intercooling from 2 to 3. And then there is a compression again from 3 to 4. So what it means is that 1 to 2 is a compression at lower pressure. It's a low pressure compression in a low stage compressor, okay, or a LP compression. And 3 to 4 is the high pressure compressor. Okay, and 2 to 3 is the intercooling. Now, what is the advantage? The advantage is that instead of compressing without intercooling, if you had compressed it directly up to a pressure 4, so this would have been the diagram. Okay, from 1 to 4 dash. Okay, so if you look at this diagram, what I had written is the area behind 1 to 4 dash. What it would be is, because it is an open system, the compressor is open system, the area behind the curve on a pressure volume diagram would represent the work input to the compressor. Similarly, area behind 1 to 2 would represent the work input to the low pressure compressor, and area behind 3 to 4 would be the work input to the high stage compressor. So if you look at this geometrically, the pressure volume diagram, one can but conclude that the area behind 1 to 4 dash is greater than the summation of the area behind 1 to 2 and area behind 3 to 4. What it means is that it shows us the advantage of going for a two-stage compression with intercooling. Okay, so this understanding we had gained when we had studied compressors. Anybody who is exposed to the theory of compressors will know that intercooling, and we had talked about the reciprocating compressors, intercooling would facilitate the reduction in compression work. Okay, this is generally a theory for compressors. So this also is applicable. This also is applicable in case of refrigeration system. Now, how is the intercooling achieved? How is the intercooling achieved in case of a refrigeration system, especially when you are talking about the multi-stage system. Okay, so let me consider, okay, let me take a new slide here now. And let me consider a case where you are having a two-stage compression system with intercooling. Now, as I said, the intercooling could be either by using some liquid like water, or there is an interesting case where we can use a flash gas for intercooling. Okay, now what is this flash gas and what is this flash chamber? We would be seeing in short. Okay, so the flash gas is used for intercooling. Why do we intercool? As I said, intercooling is desirable in many cases wherein one can expect the reduction in the work input. We would say that we would be seeing a practical application of this, and we will also discuss a practical case as to when this is desirable and when it is not desirable. Okay, so let me draw a schematic. Where I will be showing you how intercooling is done using a flash chamber. So before that, let me just draw what is a flash chamber. Okay, so this, let us say that what is seen in front of you, what I'm trying to figure out is the working principle of a flash chamber. What is this flash chamber? What is this flash tank? It is a tank, it is a chamber which has got the refrigerant in it. Okay, it has a liquid refrigerant up to a particular level. Let us say that this is a flash tank and there is a liquid refrigerant in it. Okay, liquid refrigerant in it. Now what is done is let us say that we need to intercool. Okay, we need to intercool the refrigerant. Okay. So, and we are using a two-stage compression. So this is, let us say that this one, the one which I'm drawing here, let us say that this piece which I have drawn now, let us say that this represents a LP compressor. Okay, LP means what? Let us say that this is a LP compressor. LP means a low pressure compressor or first stage compressor. Okay, and we know that the refrigerant would enter this LP compressor from the evaporator. Okay, so let us say that the gas is entering from the evaporator, the refrigerant gas which is evaporated. Okay, so from the evaporator, the refrigerant would enter the low pressure compressor. And let us say that we bubble this refrigerant. The discharge from the LP, we bubble it into the flash chamber. Okay, so let us draw this a bit neatly. So let us say that this is one is the suction to the compressor, and two is the discharge of the low pressure compressor. So the refrigerant enters the low pressure compressor, it gets compressed, as a result of which its temperature would increase. This is a high temperature gas. Okay, why this is high temperature gas? This is because of compression. Okay, high temperature refrigerant gas. This gas, when it is bubbled into this flash chamber, what you would expect is the flash gases are evolved. The flash gases are evolved. Okay, so here you have the flash gases, and let us say that evolved, plus you have the refrigerant which is going to enter the high pressure compressor. Okay, so let us say that this combination enters the refrigerant. Flash gas is also a refrigerant, but the refrigerant which is to be sent to the high pressure compressor, let us say that this is the high pressure compressor. So what has happened meanwhile? Let us try to figure out what has happened. So suppose this is a high pressure compressor. So this gas, when you are bubbling it, When you are bubbling this high temperature gas, this gas would get cooled. This gas would be cooled, and this cooled gas would be now, this would be, let us say, a saturated, a dry saturated refrigerant. There is a complete intercooling. I'm assuming that there is a complete intercooling. Okay. So dry saturated refrigerant gas, okay, because of this bubbling of this high temperature gas into the flash chamber, would enter the high pressure compressor. So this is now cooled. Okay, there is a perfect intercooling, and this is cooled. Okay. So what we have achieved is by using this flashing phenomena in the flash chamber, we have achieved the intercooling of the refrigerant from 2 to, let us say, 3, from 2 to 3. If you want to represent this on a pressure enthalpy diagram, it would look somewhat like this. This is the pressure, this is the enthalpy. Okay. So if I want to represent this on a pressure enthalpy diagram, it might appear somewhat like this. Okay. What are we discussing? We are discussing intercooling using a flash gas. So what we have is, we are having first a low pressure compressor, then you are having an intercooling, that is, there is a perfect intercooling, and then you are having again the compression up to the condenser pressure. So this way, somewhat like this, would be the picturization of this, a representation on this pressure enthalpy diagram. So using my nomenclature, this would be 1, 2 would be superheated high temperature gas, and 3 would be the refrigerant which is cooled because of bubbling into the flash chamber. There is intercooling, 2 to 3 is intercooling, and then this would emerge out at 4. So this is 4. Okay. So this is one way of achieving intercooling. The other way of achieving intercooling is outside the flash chamber. Okay, so let us represent this also. So let me draw another diagram which shows another arrangement of intercooling of the refrigerant from the low pressure gas. Okay, so how is this happening? So we have, again, I am drawing a schematic of a flash chamber. This is a flash chamber. Let us say a flash chamber having a liquid refrigerant in it. Okay. And let us say that the flash gases are evolved. How these flash gases have come, that we'll see later. The flash gases are evolved from this flash chamber. These flash gases are removed, and these flash gases, they mix externally with the refrigerant gases coming from the low pressure compressor. Okay, so this is a low pressure compressor. What we are expecting here is the following. So as you see over here, what is happening here is the different way of cooling the refrigerant which is emerging out from the low pressure compressor. And what is happening here is not only that, this arrangement has a special arrangement of flash gas removal. Okay, I will explain you what this flash gas removal is. But this flash gases which are removed, they mix with the LP gas with the refrigerant gas coming out from the low pressure, and this mixture, this cooled gas would then enter the high pressure compressor. This is a cooled gas. This is the superheated gas which is emerging out from the LP compressor, and because of the mixing of the flash gas which is removed from the flash chamber, there is an intercooling, and this intercooled gas would then enter the high pressure compressor. Okay, what is happening at the other end? So there is an entry over here from this. This is from the evaporator. From the evaporator, it is entering. The arrow has to be shown upwards. The refrigerant is entering from the evaporator into the low pressure compressor. The refrigerant would become superheated because of compression, and the flash gases which are removed from the flash chamber, they mix with the gas which is superheated, and there would not be a perfect cooling, but there will be some intercooling, and this gas would then enter the high pressure compressor. If I want to represent this, on a pressure enthalpy diagram, this is now an interesting pressure enthalpy diagram. So look at this, what is happening. Okay. So let me represent this. Suppose we again using the same nomenclature, this is 1, this is 2. After mixing, this is 3, and after compression in high pressure, it is 4. So this would look somewhat like this. So this is a pressure line. The vertical is the pressure, the horizontal is the enthalpy. This is the pressure, this is the enthalpy, this is the vapor dome. Okay, and this is the lowest pressure, that is suction pressure of the evaporator. This is your 1. 1 to 2 is compression up to the intermediate pressure. Intermediate pressure is the flash chamber pressure. Then there is a mixing of flash gas, as a result of which there is slight desuperheating or cooling up to 3, and then there is a compression again up to 4, and finally this would go to the condenser. So this is how this has to be represented. Now if you look at this diagram and compare it with the earlier one, so this is also flash intercooling. This is also intercooling of the refrigerant, but this intercooling is not a perfect intercooling, because in this case what is achieved by external mixing of the flash gas with the gas which is superheated. Okay, now this, if you want to go back and come out this saturated curve, we need to use another intercooler which is called as a water intercooler, that we would explain later. But this arrangement also is one arrangement of achieving an intercooling. So there are two arrangements of achieving intercooling. One, as I said, that we can bubble this straightway into the flash chamber, and the other is, as we have seen now, that we would have an external mixing of the flash gases. Now, how these flash gases have been removed? These flash gases have been removed because of the refrigerant which is bubbled into this, which is expanded in this expansion valve 1 up to a flash gas chamber pressure, and then what is happening is, you are, because of this is at a high temperature, so because of this entry, this is the entry of the expanded vapor. The vapor is expanded in the expansion valve 1. They enter at high temperature into this liquid refrigerant, as a result of which flash gases are generated. And these flash gases which are evolved, they are then responsible for cooling this. So where these flash gases are coming here? Because we are not bubbling the gas which is superheated in the LP compressor into this flash chamber. We are instead sending the refrigerant from the condenser into the expansion valve 1, and this high temperature gases, it's actually a liquid plus gas combination entering this flash chamber, and this vapors are removed, and what is left is the liquid. So this arrangement also achieves what is known as flash gas removal. Okay, so this arrangement also achieves what is called as flash gas removal. And interestingly, if I want to represent what is happening here on this side, it would be somewhat like this. So you are having an expansion up to the intercooler pressure, the flash chamber pressure, and then you are removing these flash gases. Okay, these flash gases are removed, and what is left here is a liquid, total liquid, which is entering the expansion valve 2. Expansion valve 2, what is entering is the total liquid. So this portion is representing the liquid. So this is a very fantastic arrangement. This arrangement achieves two things. One is it achieves the intercooling. This achieves the intercooling and all the associated advantages of intercooling, and it also prevents what is known as the throttling losses. Okay, what are the throttling losses? We had mentioned the throttling losses. So this arrangement achieves intercooling and prevents the throttling losses. So let me write down these words, throttling losses, and explain you this.
a bit. So this throttling losses are prevented, okay, are reduced because of the arrangement which is shown here. What is the arrangement? Arrangement is we are using two expansion valves, we are throttling it in two stages, and the throttle vapors are the flash gases are removed by this arrangement. Now what happens because of this is, let us say that I will call this as some phi. Suppose this is your phi. If this is phi, then this would be phi because it's coming from condenser. This would be, let us say, 6. So this is 6 here. 5 to 6 is an expansion valve 1. 7 is the entry to the expansion valve 2. This is 7. And 8 is the entry to the evaporator. 8 is the entry to the evaporator. Now look at this very carefully. If you had not removed the flash gases, the expansion would have been from 5 to, let us say, some, let me draw this carefully. Instead of 6, it would have been some 6 dash. So this, if you draw vertical from 5 and it would end at 6 dash somewhere here. So this arrangement of expansion from 5 to 6 dash would be the expansion arrangement when you are having an expansion in a single stage instead of the two stages. And as a result of which, what would be left is you would be left with a very high quantity of flash gas. When a high quantity of flash gas is a loss, because that flash gas does not participate in the evaporation process. If it does not participate in the evaporation process, it is a loss because that would require a higher size evaporator, or it would require, or it would reduce. If you use the same size evaporator, it will reduce the refrigerating effect, the capacity of the machine. Okay. Moreover, the flash gases are unnecessarily expanded. Okay, and we need to compress it back. So that is also going to add to the compressor power. So throttling losses are what? If you are expanding it from P back to the lowest pressure. So the flash gases, if they are not removed, what would happen is that these flash gases which are associated with 5, they would be expanded up to 8, and this flash gases would again need to be compressed, and they are not participating in the refrigerating effect. Okay, and when they are not participating in the refrigerating effect, they are adding to the compressor work, and they are adding to the compressor work as well as they are reducing the refrigerating effect. So that is, it would reduce the coefficient of performance. So flash gas removal is always necessary. Okay, flash gas removal is always necessary. Intercooling may or may not be necessary. What I mean to say is that when you are using an intercooling kind of arrangement, what happens is that in intercooling, this mass which is over here. Okay, so suppose this is M and M dash. So because of the flash gases, M dash happens to be greater than M, and if M dash happens to be greater than M, the compressor work in the high pressure compressor would be more because of the higher M dash, and this might reduce the overall compressor. This might increase the overall compressor work as compared to a single stage. This happens especially when you are using a refrigerant which is having a lower latent heat. Let us say like R12. If you are using R12, and if you are having more flash gases, if there is more flash gas, and if there is a more flash gas, then M dash would be much greater than M, and whatever gain we have got, so what is the gain we get because of intercooling? We had gain in terms of reduced enthalpy drop. Okay, enthalpy gain in the compressor. So whatever gain we are getting in terms of enthalpy difference, okay, that is nullified because of increase in the mass flow rate. So flash gas removal is always desirable, but flash intercooling would it might, I'm not saying always, it might increase the overall compressor work. Okay, so this we need to understand very clearly that intercooling, though theoretically, is desirable. Okay, but sometimes, especially we are dealing with the refrigerants which would generate more flash gases. In that case, we need to be careful about using the intercooling. When you are talking about flash gas removal, they are, whether you are talking about refrigerant which is having a lower latent heat or a higher latent heat, in either case, the flash gas removal would be desirable, because as you see from this figure, this is essentially going to increase the specific refrigerating effect and reduce the power consumption. Okay, the coefficient of performance would improve. So with this understanding, we would stop this lecture for now. We would just quickly recap what we had explained. Okay, uh, first thing what I had explained here is what is a multi-pressure system. In this lecture, we have discussed a bit about what is a multi-staging compression system, and I had shown you an arrangement where we can use an intercooling with two compressors. Simultaneously, I discussed a case where we talked about flash gas removal and we talked about flash intercooling. Flash gas for intercooling was discussed, and we said that this may or may not be desirable. And we talked about flash gas removal, which we said is useful for intercooling as well as it reduces the throttling losses. So always when you are using this arrangement is always a very desirable arrangement. Okay. So with this, we would be uh, stopping this lecture. Okay, if you have any doubts, you have my email ID and my phone number. Okay, it is always shared with you. So thanks a lot. Let me just write down my phone number and email ID before we stop this lecture. This is my email ID in case you have any doubts. mnshalar@kkbag.edu.in. My cell number happens to be 89220-52351. Thanks a lot for giving this opportunity of explaining this concept. Have a good day.